Have you ever wondered how language actually works? I don't mean English or Spanish, but the very idea of language itself. Today, we're going to build one from the ground up. We're going to see how, with just a few core parts, we can piece together a whole machine that can create infinite meaning.
And that really gets you thinking, right? How can something so huge and creative as a language, with all its endless possibilities for new sentences, actually come from just a small, finite set of rules? Well, that's the big question we're going to tackle.
All right, so here's our game plan. We're going to start with the absolute basics, the atoms of communication. Then we'll build the engine that puts them all together, which is the grammar. We'll even see what happens when that engine kind of glitches out, with something called the ambiguity problem. And finally, we'll organize this whole shebang by climbing the very cool Chomsky language ladder.
Okay, first things first, before we can build anything, we need some raw materials. And in the world of language, that means symbols. So, the very first piece of our language machine is the alphabet. And forget ABC for a minute. In this world, an alphabet is just any limited set of symbols. Seriously, think of them like the unique Lego bricks we get to build with.
And these symbols can be anything. An alphabet could be just 0, 1, or it could be a wild set of abstract shapes like you see here. The machine doesn't care what they look like, only that they're all different from each other.
So once we have our alphabet, our set of atoms, we can start snapping them together to form molecules. And we call these words. A word is literally just a sequence of symbols we picked from our alphabet. It's that simple. And when you gather up a bunch of these words, you get a language. See, a language is just a specific set of words that we've decided are valid. Think about it. With the alphabet A, B, C, you could make an infinite number of different strings. But a language, like English, says only some of those are actual words. So the real challenge becomes, how on earth do you define that group of valid words, especially if it's infinite? And that question, well, it leads us right into our next big idea, the grammar blueprint. This is the answer. It's the finite set of rules we can use to generate an infinite number of valid words. So yeah, this is the crucial problem, isn't it? You can't just write down an endless list of all the right sentences. That's literally impossible. What you need is a compact, powerful system for generating them. You need an engine. You need a grammar. And here it is, the blueprint for that engine. It's got 4 key parts. First, you have terminals, T. These are our final building blocks, the actual symbols that show up in the final word. Then you've got non-terminals, N. Think of these as temporary placeholders or variables, like noun or verb, that we need to replace later. S is the special start symbol. It's the one single command where every single sentence creation begins. And finally, you have P, the production rules. Now, this is the heart of the machine. It's the instruction manual that tells us exactly how to swap out our variables until we're left with a finished word. So, how does this machine actually build a word? The process is called derivation, and it really is just like an assembly line. You always start with that S symbol. Then you pick a production rule from your list and make a swap. You look at your new string of symbols, find the next variable, and you replace that one. You just keep doing this over and over until all the variables are gone, and what you're left with is a finished word made of only terminals. But this whole mechanical process, it's not always perfect. Sometimes the blueprint itself has a flaw, which brings us to the ambiguity problem. So let me ask you this. Is it possible for one single word, generated by the same grammar, to have 2 completely different internal structures? Like, can it be built in 2 fundamentally different ways? The answer is a definite yes. It's pretty wild. Take this grammar here. The rule basically says our start symbol S can become ASBS or BSAS, and so on. Using these rules, we can totally make the word ABAB. But the really fascinating part is that there isn't just one way to do it. There are at least 2 completely different sequences of substitutions that gets you to the exact same final word. We can visualize this whole process with something called a derivation tree, like this one. So the first way to create ABA goes something like this. S becomes ASBS, which then becomes ABS, and you keep going until you finally hit ABA. All the leaves of the tree, read from left to right, spell out our word. This gives the word one possible structure. But check this out. Here's a second derivation tree. It also spells out ABB at the bottom, but its internal branches, its fundamental shape, are totally different. So we have one word, built from one grammar, but it has two different structural meanings. This is ambiguity. And for a computer trying to understand code, two different meanings for the same command, well, that can be a complete disaster.
So it turns out that the kinds of structures a grammar can build and whether or not it can be ambiguous, it's all related to its power. And this brings us to our final section, this beautiful classification system known as Chomsky's language ladder. Back in the 1950s, the famous linguist Noam Chomsky realized that you could classify all these formal grammars into a super neat hierarchy of just 4 distinct types, where each one is more expressive and more powerful than the one below it. And here is that ladder. At the very bottom, you've got type 3, regular. These grammars have the simplest, most restrictive rules possible. One step up is type 2, context-free. And the name is a huge clue. The rules for replacing a variable don't depend on its context or its neighbors. By the way, this is the level where our ambiguous grammar from before lives. Climbing higher, type 1 is context-sensitive. Now the rules can depend on the symbols around them. And at the very top, type 0 is unrestricted. It's the Wild West, basically anything goes. As we climb this ladder, the rules get looser, and the power to describe really complex patterns just goes way, way up. So a type 3, or regular language, is the simplest kind. Its grammar can only produce really simple linear patterns, like any number of A's followed by any number of B's. But it can't do things like make sure the number of A's and B's are actually equal. It just can't count. To do that, you have to climb to type 2, a context-free language. This grammar is powerful enough to generate strings with an equal number of A's and B's. This ability to create these nested, balanced structures is absolutely crucial for things like programming languages, which have to match up all their opening and closing brackets perfectly. And for even more complexity, you need type 1 context-sensitive. What if you need the number of A's, B's, and C's to all be equal? Well, a context-free grammar just can't handle that. You need rules that can actually look at their surroundings to coordinate the whole process. And that's exactly what a type 1 grammar gives you.
So we've gone on this journey all the way from simple symbols to this really elegant hierarchy of computational power, which leaves us with one last, really fascinating question. We've managed to neatly sort all these formal machine languages onto a ladder. But where do our own natural human languages fit in? Is English a type 2 language, a type 1? Or does it need a kind of power that's completely off this chart? Now that is a deep question that linguists and computer scientists are still trying to figure out today.